Hello, we're going to begin our discussion of the first chemical system that we're going to solve with quantum mechanics. So we're going to talk about atomic structure, and I'm going to hook up the camera. Okay, so this is focus 8 in your textbook, and I'm assuming that even if you can't read what's on my screen, you can follow along in your own textbook. We'll go through just section A, which is really quite long. It's on atoms that are like hydrogen. So any atom or cation that only has one electron is a hydrogenic atom. So you could have hydrogen with one electron, you could have helium plus one, but each of these one electron atoms are the only systems that you can solve completely exactly with Schrödinger's equation. So we're going to first look at that in detail. And then the next section will move on to how do you deal with more than one electron, because those systems, immediately you have to start making approximations. So the permitted energies were known experimentally. So at this time we have emission spectroscopy where we see that only certain lines, so right here this is the spectrum of hydrogen in figure 1, and it's showing you that there are only certain lines or certain frequencies or wavelengths of light that are emitted from hydrogen when you excite it. So you pass electricity through hydrogen atoms, the electrons absorb some of that energy, and when they fall back down to their ground state, they give off characteristic frequencies that are discrete. They're not continuous. Doesn't give off every kind of energy. So we want to think about what that means. So Rydberg came up with an equation that showed that these fundamental frequencies that are given off by hydrogen can be related to integers. So the frequency is proportional to, in this case, in the Balmer series, where you're starting in the n equals 2 state, it's proportional to 1 over n squared, or 1 over 2 squared, 1 over some other integer value squared. So you're going from the second state to some other n state in the Balmer series. The Pascal series had a similar structure, and it turns out that the lines in these series, they were given names. Lyman's series would be you start in the ground state. Balmer is where you start in n equals 2. Paschen, where you start in 3. Bracket, where you start in 4. And P-fund, where you start in 5. So I wouldn't ask you to remember those, but just to realize that the reason the series are different is because you're starting in a different state. So Rydberg figured out that it was proportional, the frequency of each of those emission spectra peaks was proportional to 1 over the difference between integers squared. And so he used the spectra and figured out what's called the Rydberg constant, which has this numerical value right here, 109,677 in units of reciprocal centimeters. So these are wave numbers. And so these frequencies have to be equal to the energy difference between the states that the light is being, or that the electron is taking transitions from. So if you're going from one state to another, you'll have a difference in energy, and the type of light that's given off is equal to a photon's energy equal to that separation, that delta E. So that's Bohr's frequency condition that we learned about a little bit earlier. So when we want to solve this with Schrödinger's equation, first thing we have to do is figure out what the potential energy function is. So equation 3 tells you that the potential energy is a function of R. It's just a function of how far the electron is from the nucleus. Z is the integer charge on the nucleus. So if it has 1 proton, it's 1. 2 protons like helium, it's 2. E is the charge on the electron, so it's the fundamental charge over 4 pi, and epsilon 0 is the permittivity of a vacuum, so that's a constant from physics. So we're gonna use this with our kinetic energy operator, and you're not gonna go through the solution, but if you take 367, we'll go in more detail into how this problem is solved, but right now we're just gonna look at the solution. So on the top of page 467, it talks about some important properties. So the wave functions, the solutions of the Schrodinger equation for an electron in the presence of a nucleus has to satisfy certain conditions in order to be acceptable. So we learned about that in focus 7. There are certain boundary conditions. So for a hydrogen atom, these boundary conditions are that the wave function has to decay as r goes to infinity. That makes sense. As r gets infinitely far from the nucleus, if it's a hydrogen atom, you're not going to be able to find the electron out there. And it must repeat itself just like the particle on a sphere, except now we have 2 different boundary conditions. It has to repeat itself as it goes around the equator, and then also the other angle as it goes 3-dimensionally around the poles. So you're going to end up with 3 quantum numbers because of those 3 boundary conditions. Has to go to 0 at infinity, has to repeat itself as the angle repeats itself. And so when you solve that, you end up with these allowed energies. So the energies are negative, and the energy is a function of n because of that quantum number having a boundary condition. So it's Planck's constant times the speed of light times the Rydberg constant for whatever nucleus it is, times the charge on the nucleus in an integer value squared, divided by some quantum number squared. So those quantum numbers can take on values of 1, 2, 3, up to infinity. The Rydberg constant, as a function of what nucleus it is right here, and this is the reduced mass. So this is essentially it's what's moving in the system. The nucleus is pretty stationary, and so the reduced mass is the relative motion of the electron to the nucleus, and so what mass is actually moving. So the nice thing was that when you solve Schrodinger's equation and get this Rydberg constant, Schrodinger must have been thrilled, it says, to find out that when he calculated RH, the Rydberg constant for hydrogen, the value he obtained was almost exact agreement with what they had found experimentally. So the solution from quantum mechanics was giving almost exact correspondence to what they found experimentally, which is pretty magnificent. So the most important features of this equation that we just looked at, the energies for the hydrogen atom, are the role of n, so there are only certain energies allowed. The significance of the negative sign, which is just that it has negative energy relative to the electron and the nucleus being infinitely separated. So it's more stable than a free electron in a free nucleus. And then the appearance of the z squared makes sense that the energies are going to depend on the charge on the nucleus. So this is just a picture of what the energies look like. So at low quantum numbers, the states are far apart. You go further and further up, they get closer and closer together. That's an example of Bohr's correspondence principle. So as you go up, the electron can have a continuous rather than discrete amount of energy. This equation over here compares the energy of 2 states, which is what these, when you have the energies, then to understand what frequency of light would be given off. For example, if you're going from the 2 back down to the 1, this just takes the difference of 2 states and shows you that it's also a function of quantum numbers. So self-test 8A.1 just asks you if you have a transition in the bracket series of lithium 2+, and the wavelength of that transition is 450 nanometers what's the quantum number of the upper energy level? So I looked up in that little set of definitions of what each series is. The bracket series, the state you're starting in is n equals 4. So I plugged it into this equation that looks at the difference between the energy of two states. So that would have been this equation right here in your text. And if you look at this, if this is an energy, if you divide by hc, then you get 1 over lambda. So we have the wavelength, so we can put 1 over lambda in here if we divide each of these by hc. So 1 over lambda equals Rydberg's constant times the difference in 1 over the quantum number squared. We want the Rydberg constant for lithium 2+. So it's what it would be for hydrogen times z squared. Yeah, this z right here. So this z squared has to come into play because we're not dealing with hydrogen. So take hydrogen's constant multiplied by 3 squared because lithium has a +3 charge on it. We end up with energy should be equal to negative hc, Rydberg constant, z squared. Whoops, we don't end up with that. That's what we used, I'm sorry. Used to get this. So this combination will be the Rydberg constant for something other than hydrogen. So they gave us a wavelength of 450 nanometers. So I changed that into centimeters. So 1 over the wavelength in centimeters is equal to the hydrogen Rydberg constant times 3 squared because it's lithium, times 1 over 4 squared because it's the bracket series and we're starting in n equals 4. And we're trying to figure out where it goes to. So when I did that math, I ended up with x equals 5. And so this transition is from n equals 4 to n equals 5. Okay. So now these are a lot of things that you know from Gen Chem 1. For example, ionization energy. The energy it takes to completely remove an electron from an atom or ion. And so if we're talking about hydrogen, if it starts out in its ground state, it would be the energy it takes to go from n equals 1 up to n equals infinity. So n equals infinity would just be a high state where the electron no longer is interacting with the nucleus. So that one's pretty easy to do. I'm just trying to find the paper that I did that problem on, this self-test. So self-test 8A.2 says, what's the energy required to ionize a hydrogen atom initially in the first excited state? So we will plug that in. So we have the difference in energy between two states is Hc. It is the hydrogen atom, so we use the Rydberg constant for hydrogen. We start in the first excited state, n1 is 2, so 1 over 2 squared minus 1 over infinity squared, because we're going from n1 equals 2 to n2 equals infinity, where it's separated. And you end up, if you don't put the numbers in, but just as a function of Rydberg constant, the difference would be 1/4 Hc and the hydrogen Rydberg constant. So we look at the wave functions in a little more detail. So the quantum numbers we end up with, we call n, l, and m sub l. So we saw already that the energy that comes out of Schrodinger's equation for the hydrogen atom is only a function of one of those quantum numbers, the n quantum number. And the other two tell us something about the angular momentum. So the total wave function is given here at the bottom. Turns out if you take this problem, the reason you can solve it exactly is because you can separate the variables. So you couldn't solve this problem if you worked in Cartesian coordinates, because the potential energy would be a function of x, y, and z for the electron. But if you go to spherical polar coordinates, then the potential energy is a function of r, how far the electron is from the nucleus, but it's independent of the angle around the nucleus because there are no particles for it to run into, essentially. So we can separate the wave function into the r part and the angular part, and then we know that the whole wave function is a product of those two. So we call these the radial wave function and the angular wave function, which makes sense. So the r part is the part of the wave function that depends on little r, and y, which we actually solved for in the last chapter, is the angular momentum wave function. So you can solve this problem exactly because you can separate it from a partial differential equation into an ordinary differential equation, where each of those is just a function of one variable. So let's look at this next self-test. So now we want to think about the quantum numbers, and these rules are exactly what you would have saw in Gen Chem 107, that says the principal quantum number n can have values 1, 2, 3, up to infinity by integers. L is a function of n, so it can be 0, 1, up to n minus 1. And m sub L can be 0, plus or minus 1, all the way to minus L and plus L. So we remember the n quantum number tells us which period we're in the periodic table. The L quantum number tells us the shape of the orbital. Remember, when L equals 0, we called it S. When L equals 1, we called it a P. And then the m sub L tells us the projection of that angular momentum on some arbitrary axis. So you can have total angular momentum, so the electron has angular momentum around the nucleus, but the projection of that can be different orientations in space. And so the m sub L is a function of L, so how many projections of that you can have with different magnitudes is a function of what the total angular momentum is. So because of that, this self-test at the bottom of the page is asking us to specify the orbitals with n equals 3. And so before you look at the answer, if n equals 3, then n equals 3, then L can be anything from n minus 1 to 0. So we have a 2, 1, and a 0. And because how many of the m sub L's you have depend on L, it's 2L plus 1 because it's the negatives and the positives plus 0. So for example, if L equals 2, m sub L equals m sub L can be 2, 1, 0, minus 1, and minus 2. So 2 times L for the pluses and minus, and then plus 1 for the 0, 1. So we will have 5 d orbitals. So 5 orbitals where L equals 2, 3 where L equals 1, and 1 where L equals 0. So this table on page 360 is where you're going to go if you're asked for one of the radial wave functions. So if you're asked to describe, for example, a 3p orbital, you'll go here and you'll look for the part of that wave function that describes the function as a function of little r, the distance of the electron from the nucleus. So an important thing that you probably didn't focus on in 107, or it's really easy to miss because you go right from here into the periodic table and you talk about orbitals and other atoms. But it's important to realize that it's only hydrogenic atoms where all orbitals with the same value of n, but different values of L and M sub L have the same energy. So that would mean for the hydrogen atom or a hydrogenic atom or hydrogenic system of any sort, could be a cation. If you have s orbitals and p orbitals with the same n value, they have the same energy. Or s's, p's, and d's, they all have the same energy. We know as you go up the periodic chart and you get to helium and anything bigger, the s's and the p's and the d's and the f's shift in energy and they're not the same. But for a hydrogenic atom, they're the same. So that means we have degeneracy, which is pointed out in this diagram here, that in the K shell, where n equals 1, which is just listed right here, we have 1 orbital. When we have the L shell, when n equals 2, we have s's and p's. So we have 4 degenerate orbitals. So as you go up, if all the different L values have the same energy, your degeneracy goes up at the same time. So some important things to think about: the average distance from the nucleus increases as n squared in accordance with what's expected. So as the quantum number gets bigger, the electron is further from the nucleus. For a given n, L, the mean distance decreases with increasing z. The electron is drawn closer to the nucleus as the latter's charge increases. So that is harder to see mathematically, but that tells you that for a p orbital, the mean distance or the average distance from the nucleus decreases if you increase z. So the mean distance depends on L. With high L orbitals closer to the nucleus, the dependence is weak on account of the n squared in the denominator. So that makes it L not as important. So these are things you definitely remember. We call things shells when all the electrons are in orbitals of the same n value. This just tells you n equals 1. These were given letters, K, L, M, and N. And then we have the subshells. Within a shell, all of the orbitals that have the same L value. And then this is something you should remember. When it's an s orbital, we have 1, P, 2, 3, D, 5, F, 7. So this self-test, what subshells and orbitals are available in the n shell? So that's pretty easy. I don't think I even did that one. So if we go to the n shell, n equals 4. What did I do? I remember writing this down. Yeah, I did do it. So if n equals 4, then we can have L equals 3. So n minus 1 down to 0. So we'll have 3, 2, 1, and 0. So we're going to have f orbitals. There'll be 7 of them. D orbitals, 5 of them. P orbitals, 3 of them. S orbitals, 1 of them. So when we look at the s orbitals, they're spherically symmetric about the nucleus. So when we look at each of their radial wave functions, they'll look very similar to this. This constant in here, A0, is called the Bohr radius. It's the most probable place to find an electron in the hydrogen atom, so it's given its own definition. So, symmetric. there are different ways to represent the orbital. So it's a function. So you could graph and see with just changing the shade where the most probable locations are. So in the S1s orbital, gets less and less as you go away from the nucleus. This shows you that in a 2s, you actually have a radial node. So you move away from the nucleus, you have a radius at which there's 0 probability, and you'll add one of those every time n increases. That's just showing it. What we're more used to is showing the shape of an orbital by a sphere, and this sphere represents where you'll 90% of the time find an electron. So it's a boundary surface that captures 90% of the probability. So remembering that each of these functions tells you the probability of where you're going to find an electron. Okay, so we're going to use the wave function for hydrogen to solve the self-test 8A.5 on page 363. So we have to look at the illustration first. So the illustration says the probability of finding the electron in a volume of 1 picometer cubed centered on the nucleus in a hydrogen atom is calculated by setting r equals to 0, because that's the location, and the expression for the wave function. And then we'll solve that and then take the volume. And what's the question? Okay. So I thought it was going to do a relative one. So we're just looking at the probability of finding the electron at the nucleus. So now we want to look at, in the self-test, how likely is it to find it at the Bohr radii? So the Bohr radii is that A0. So the wave function for 1s orbital, they gave us, so it's 1 over pi, Bohr radii cubed, and then 1/2 of that, or it's to the 1/2 power, and then e to the minus r over A0. So if we want to know what the probability the wave function squared is when we're at A0, then we set r equal to A0, so that's 1. So and so we end up with e to the minus 2. So when I squared this, remember when you square an exponent, something with an exponent, you can add the exponents. So e to the minus r over A0 squared becomes e to the minus 2 r over A0. R over A0 at A0 equals 1. So we end up with the probability being 1 over pi. So I squared this term out front to get rid of the 1/2 when we squared to get the probability. So we end up with 1 over pi A0 cubed, e to the minus 2, and we want to know in some small volume, 1 picometer cubed. So if I put A0 in picometers, that's the only thing with units. This whole thing has to be unitless because it's a probability. We end up with A0 equals 52.9 picometers, which was given in the problem before. And so when you plug in, you end up with 2.9 times 10 to the minus 7, or chance of about 1 in 3.4 million times. If you look for the electron, you'd find it in that position in space. So that's pretty small, and the most probable location of finding the electron in a hydrogen atom is at the Bohr radii. But when you think about it, when you're at the nucleus, there's 1 point. But when you're at the Bohr radii, you have a whole surface of a sphere, all at that same distance from the nucleus, that is proportional to the probability of finding the particle at that radius, not at a particular point, but anywhere in a sphere at that radius. And so the probability function ends up being r squared, little r squared, times the radial wave function squared. Essentially, that r squared comes from, that's proportional to the surface of that sphere. So this is just showing that you go through a maximum at A0. That's the maximum location to find a particle or an electron in a hydrogen atom. So when we look at the next example, we want to consider, let's see, yeah. So we're going to do an analysis that says do the same thing for 2s orbital. And so we have to read through what they asked for the question for a 1s orbital. So they say, consider an electron in a 1s orbital of a hydrogenic atom of atomic number Z. Calculate the probability that the electron will be found anywhere in a shell formed by a region between a sphere of radius A0 and a sphere of radius 1 picometer greater. So they're showing you in this picture just that little layer of density at A0 up to 1 picometer bigger. Then we're going to set Z equals to 1 and actually get a number. What they do in this problem, which is a hard thing for you to think about when it's valid, so I'm going to solve this problem a different way. They say that the function is a constant from A0 up to A0 plus 1. And so they don't integrate. They just calculate the function's value at A0, say it's constant, and multiply by the volume. We're going to do it a little differently. So now when we have a 2s orbital, we want to solve the same thing. We want to know the probability of finding it in that sphere. So I'm going to integrate. And by integrating, I'm saying, I'm not sure if r stays constant. I'm not sure if 1 picometer is a great distance away. It would be if the function was very peaked at this location. So I'm going to say I'm going to integrate over the probability function from A0 up to A0 plus 1. And so the r, the radial wave function for the 2s electron is given in that table. So I wrote it out. I'm going to set Z equal to 1. And now I'm going to plug this into Mathematica, and we're just going to integrate that. So let me pull Mathematica up on my screen so I can show you how I put it in. So I cleared the value of A0, which is an important thing. You'll learn about this as you work through the tutorials for Mathematica. But anytime you use a parameter, who knows? Sometimes Mathematica remembers from the last time you were here. So I always clear the value. So it starts out thinking A0 is just a parameter with no value. So now I'm putting in, whoops, I better share my screen again, sorry. You can't leave it shared. And every time I go from shared screen to shared screen, it's really easy to forget. Okay, so now hopefully you can see this. So okay. So I'm going to put in exactly what I had on my sheet. I'm going to put in r squared times the wave function squared. I'm going to integrate over little r. So I'm integrating over that distance from A0 up to 1 plus A0. So those are my limits. And I set this up by using the palette. Initially, then it gives me the value of that integral. And then I tell it that A0 is 52.9. After I do that, then I can ask again. I called this integral A. So now I can ask it, what's the value of A? And I get 8.6 times 10 to the minus 4. So that's the probability you're going to find the electron in that sphere of thickness 1 picometer at Bohr radii, so at A0 from the nucleus. So let's go back to here. And what you'll see, the book, I think, got 8.4 times 10 to the minus 4 with the approximation, where rather than integrating over this, they just said that this function is a constant. So depending on how well you want to know the number, in today's age, having Mathematica means there's really no problem in carrying out a more exact calculation. And it helps you not feel like you have to know when an approximation is valid. So you can get the orbitals, the R component, the radial part of the wave function from that table. And then it also gives the radial wave functions for P and D orbitals in there. So when you look at the next illustration, the brief illustration, it wants you to locate the nodes. So from table 8A.1, you have the form of a 2p-z orbital of a hydrogen atom, so z equals 1. So you plug in the wave function, and it's a function of R. So the nodes are going to be at the places where that function equals 0. So if we do the same problem for a 3p orbital, we'll understand the mechanics of this problem. So a 3p orbital has this form. And I didn't have to care about the angular part because I'm asking about the nodes, the radial nodes. So the points at which the function is 0 as a function of R, not whether or not there are zeros at some angle. So I take the R and then I just look for the points at which the function equals 0. I also did that in Mathematica. So I'm going to go back to Mathematica and share it again. Okay, so right after the line, which was output from the last problem where we got 8.6 times 10 to the minus 4, I started a new problem, and I could have put a comment there, which I should have, that says I'm starting a new problem. So now I'm starting 8.7. I'm looking for the zeros in the 3p orbital. So first I clear the value of A0 because I don't want the answer as a numerical value. I want it as a function of A0. And then I said I want to solve for the point at which what I put in there within the square brackets is the wave function. So I typed in the wave function, and then I said equals 0. I want to solve for the points where the wave function equals 0 as a function of R. And so when I do that, it gives me the answers R equals 0, which isn't a radial node because it's just a point, but it tells me the second one is at 6 times A0 over Z. So that's exactly what the book got as well. So that's the point at which you'd have 0 probability at that radius of finding an electron if it's in a 3p orbital. So I think you can read this last page. Just reminds you of some things that you already know about P and D orbitals, something about the shape, something about the nodes, something about the shape of the p orbitals, and then remind you about the loud quantum numbers and what those mean. So I think the last page is similar to what you know from Chem 107. So I'm going to stop there, and we'll go from this first section where you could actually solve this problem exactly up to even helium, where you have to start making approximations.